homepage is there's a nice handout that Nat prepared for you. If you haven't done it and you have the opportunity to, I would suggest you print that out from the CoastLines site. Okay? And the last thing we'll do is there'll be questions, and we have some announcements for you about next week's webinar. Okay? So that's what the agenda looks like. I'm going to switch the presentation over to Sam, and I'd like to welcome you back to CoastLines. Some of you, this is the first time that you're in here. I just wanted to remind you that if you have questions, we are here to answer your questions. So even though somebody's presenting, you can use the chat window, you can use the question and answer window to send us a question, and we'll respond to you. There will also be times that we might open up the phone lines and take questions over the air. But most of the time, your lines will be muted just so that if there is a presenter talking, there's not a lot of background. Okay? All right, thank you. Sam, are you ready?
Yeah, I'm ready. Thanks, Jenny.
Okay, let me turn it to you.
So everyone, I think, Jenny, should be seeing my screen here. And if you're not, post a question in the question and answer box, and we'll make sure that you eventually are. But before we start, I'd like just to ask you quickly to think about the experience that you personally have had with GIS and GPS technology. So think maybe about these questions. Which of the following GPS or GIS technologies have you used? Have you used an internet mapping site to search for something geographically? Or have you used an internet mapping site to calculate a route distance? Have you used a GPS navigator in your car, perhaps? Perhaps you've used a handheld GPS receiver that tells you where you are and where you are in relation to other things. Perhaps you've used Google Earth, or perhaps you've used a fully functioning GIS to create maps or to analyze data that you've collected. If your answer to any of those questions is yes, then you have used a GIS and a GPS technology. And what we would like you to do over the next year is to extend your experience from users of positioning and mapping systems to creators of geographic knowledge. So how are we going to do that? First of all, let's talk about what GIS is. So GIS is actually two things. It's a tool, and it's also a science. When we think about GIS as a tool, the important thing to realize is that GIS is not a magic wand. It has 4 real and essential components. And so those are the hardware. And in the history of making maps, this is probably represented by the blank piece of paper onto which you draw a map. But in GIS, it's the computers and the disk drives and the monitors and the input devices that we use. The second component of a GIS is software, and there are many different software programs that can display and analyze geographic data. Today, we'll have a look at a couple of them and some examples of some of the GIS that are out there and the sorts of things that they can do. The third component is the geographic data itself. Geographic data is what you want to display on your map, which will depend on what question you want to be able to answer with your map. And collecting geographic data, or appropriate geographic data, let's say, could be the most time-consuming and expensive part of running a GIS project. The fourth component of the geographic information system, however, is the intelligent user, and that's you guys. So certainly it's the most important part of a GIS, and like any tool, a GIS can be used well or poorly. So our job, I guess, is to try and help you to learn how to use GIS well, to teach your students concepts, and to get them to ask and answer questions with this tool. those who enjoy using GIS as a tool to ask and answer scientific questions can also become curious about how the tool is put together. So GIS is also a scientific discipline that involves the study of organizing geographic data and of representing geographic data and also of developing new ways to analyze geographic data. So it's a tool and a science. So what is GIS then? And what do the four components of this tool do when they're used together? So the important thing about a GIS is that it links information about where things are, which we call the spatial component, with what things are like there, which we call the attributes. So the geographic component might be, for example, a city or an address or a mountain peak or a scientific sampling site, or the geographic, and these are all examples of points. The geographic component might be a line, like a road or a river or a shoreline or a political border, or the geographic component could be an area which is bounded by some sort of polygon. And something like this could represent a park or a forest or a certain type of habitat or a state or a county, etc. So each of these three components are either a point on the map, a line on the map, or an area on the map. In a GIS is called a feature. Now the attributes, the second geographic component, or the what things are like there, are connected to each feature, and the attributes are held in a table. The table of data might be as small as a single detail, or a single feature might have many different attributes that describe it. Some examples might include a point feature that, let's say, it represents a city. And the data table that's connected to that point could have the city's name, the city's population, whether it's a capital city or not a capital city, when it was founded, etc. Any information that you can attach to that city point could be included in that table. Let's go with another example. So a line might represent a road. The data table that's associated with that line could include the name of the road, what type of road it is, whether it's a highway, a street, a one-way street, an unpaved road, or a bike path. When it was last checked for potholes, or how many cars drive on it each day. If your feature was an area, a polygon, it might represent a state, in which case the table that's associated with it would include information about that state, perhaps its name, perhaps its population, its area, its primary industries, its capital, or even the way it voted in the 2008 election. Okay, so those are the two important things about GIS. We're linking information about where things are found with what things are like there. So, a GIS is, in its crudest sense, a map, but it's different from a paper map in a number of ways. The information that's displayed on a paper map is static at the time of printing, while on a digital map it's dynamic. You can use the GIS to display the information that is important to the user as they need it. For example, in the morning you might be looking for coffee shops, but by the afternoon, when you're looking for beer, you can ask the GIS to display all the pubs, and you can get rid of all the coffee shops, which are blocking your view of the map. Secondly, the information that's displayed on a paper map is limited to what is displayed graphically, while features on a digital map are backed by the tables of data that describe the feature that we just talked about. So, why is this important? The reason this is important is GIS is about finding patterns that would not be apparent in data that were displayed without a spatial component. So, the image on the slide here is a simple example. But you can see that there are different data layers that can be combined to build an overall picture of the elements that are needed to run a retail business in this case. So each layer is a slice of reality. A business owner using this map can remove information that's irrelevant, like, say, the baseball diamond here, and look for relationships between layers that might affect their business. In this case, where customers are and where buildings are available for them to use, and the streets which allow customers to get from the buildings they're in to, from their homes to the buildings that the retail business owner might want to set up shop in. So GIS is about finding patterns in data that may not be obvious in a spreadsheet. It combines, which means it combines the advantages of static maps and the data backing of a database. So when a GIS professional uses a GIS, they think like scientists, and what we want to try and do is encourage you to do the same thing. You'll notice that the cycle of geographic thinking, which is outlined here in a list rather than a cycle form, but the cycle of geographic thinking parallels the cycle of scientific thinking. So geographers ask questions, they acquire the geographic resources that they need to answer those questions, they explore geographic data, then they analyze the data to expose relationships between the variables that they're looking at, and they act upon their findings. Often findings lead to further questions, and the cycle begins again. And as with science, geographers might also find small cycles of questions that occur within a larger task. So Jenny will talk a little bit more about geographic thinking and this cycle of geographic thinking in the next section of the webinar. But I wanted to introduce it as a part of GIS, and I want you to keep it in mind as we go through certainly this webinar, but definitely the year as well. So using a GIS in the classroom, GIS is an excellent, I think GIS is an excellent tool for teaching both science content and also science practice in the classroom, because it's very good at displaying complicated data sets in visual ways. The visualization of data often leads to a better understanding of the connections between concepts, as well as physical connections between systems that are larger than a student's local sphere. The scientific thinking cycle I described in the last slide, or the geographic thinking cycle that I described in the last slide, nurtures curiosity in students. And when interest is developed independently by a student, they're engaged in the concepts they're learning, and when they're engaged in the lesson, they certainly learn more thoroughly. So the skills and knowledge that students gain through using a GIS to study a local problem empowers them to affect change in their own environments. It also allows them to see how scientists and other professionals do the same thing. So right now I'm going to switch tacks a bit and talk about the global positioning system, because the global positioning system is one of the ways that we can generate data for our maps. You'll remember the first component of geographic data is the location, and the GPS is the preeminent tool for determining location on Earth. So I'm just going to talk for a couple of slides about GPS and how it works to determine your location on Earth. I'd like to start with a basic history, a quick history of location finding, because for me it illustrates some of the problems that GPS would eventually overcome. So the simplest method of finding out where you are is to look for landmarks that you recognize and then create a mental picture of where you are based on the things that you see around you. Dead reckoning is a form of location finding, and it came to prominence when people took to the seas beyond the sight of land and obviously landmarks then. So in the process of dead reckoning, you begin by knowing where you start from, and you measure how fast, for how long, and in which direction you travel. And this allows you to determine your position relative to where you started. But the problems with this system stem largely from the instruments that used to be used and still are used to determine speed and direction of travel. And in the early days, they were very primitive and very prone to error. So next, astronomers discovered that stars held relatively fixed positions above the Earth, and they used celestial navigation techniques to help them determine their location in relationship to the star background. But these techniques were mathematically complicated, and they excluded uneducated travelers, and they depended on seeing the sun and the stars, which meant you could only be used at certain times of day and in clear weather. The next huge leap forward, I guess, in navigation was LORAN. And LORAN is a radar-based system that uses triangulation, which, let me point out, is identifying the angle between you and two known points to accurately predict your position. But the LORAN system has only coastal coverage due to the need for fixed radar stations. So it wasn't the perfect navigation system either. So in the 1970s, the U.S. Department of Defense decided that they needed to develop an even better system for determining location. The reason for this was actually nuclear in nature rather than navigational. And I can explain. During the Cold War, the USSR had thousands of nuclear warheads that were pointed at the U.S. And the U.S. had thousands of nuclear warheads that were pointed at the USSR. And both countries got really good at accurately telling those missiles where to land, provided the missiles knew where they were starting from. So the USSR had most of their missiles in silos across the country. They didn't move, and so they knew where they were, and they were then easy to aim. But the US had a huge number of its missiles on ships that were constantly moving, and so, of course, since they didn't know where they were at any one time, they were very difficult to aim. So the Defense Department invented this satellite system that would allow you to find your position anywhere on Earth in any weather at any time of day. And the first satellite for this system was launched in 1978. In 1980, the system was made available for use by civilians, and by 1994, the full system of 24 satellites and a few spares and a few ground stations for monitoring and enhanced accuracy was in place. In May of the year 2000, code in the signal was released so that the accuracy of a handheld GPS device was below 15 feet. So now we have a system that basically allows anybody to easily determine their location on Earth, which you'll remember is one of the key ingredients of geographic data. Alright, so how does this system work? Really quickly, 24 satellites are orbiting the Earth at roughly 11,000 nautical miles in altitude, and their positions are monitored by 5 ground stations, so we know where they are at any time. Each satellite is equipped with an extremely accurate atomic clock, and each satellite sends out radio waves, which a GPS receiver in your car or your hand, for example, can detect. The receiver that you're holding knows exactly when the radio waves were sent out by the satellite and exactly when it receives them. So using those 2 bits of information, it can calculate the time that the radio wave took to go from the satellite to the receiver. And then using a simple formula of that distance equals velocity times time. And we know the time, as I just mentioned, and we know the velocity, which is the speed of light that the radio wave is traveling, or 186 miles a second. So the receiver can calculate its distance from each of the satellites that it can see in the sky. And the GPS receiver finds its location on Earth by a process called signal trilateration, which you'll note is different from triangulation, which we talked about in LORAN. So let's have a look at how signal trilateration works with GPS. So in this example, you first turn on your GPS receiver, and there's a guy standing there with a GPS receiver in his hand. The GPS receiver has no idea where it is, so it starts looking for signals from these GPS satellites. In this example that I've got illustrated here, let's say it receives a signal from a satellite, and as we know, it calculates the distance from that satellite, and it calculates this distance as 10,000 miles from where the satellite is. So now the GPS receiver knows that it must be somewhere 10,000 miles from that satellite. But that location could be anywhere on an imaginary sphere, where the satellite is at the center, and there is on the image. The radius of the sphere is 10,000 miles. We calculated that, the GPS receiver calculated that distance. Okay? And so this red object here represents the sphere where that satellite could be in. But because the GPS receiver has no idea what direction the satellite is in, keep in mind. So the GPS receiver now looks for a signal from a second satellite. Okay, and let's say in this example it calculates that it is 12,000 miles from this second satellite. Okay, and here we can see the second satellite. We can see the radius of the sphere, 12,000 miles, and we see the outline of the second sphere. Okay, the receiver knows that it has to be on the surface of this second sphere, whose center is on the second satellite, and the radius of the sphere is 12,000 miles. But it still has to be somewhere on the first sphere generated by the first satellite. So there's our first satellite, our 10,000 mile radius, and our first sphere. So the only place that the GPS receiver can possibly be is on the intersection of those two spheres. And you can see that denoted in this diagram by the gold circle there. Okay? But still, it could be anywhere on this gold circle here. Alright, so what does the GPS receiver do? Of course, it looks for a signal from a third of the GPS satellites. Now let's say hypothetically that it calculates that it's 16,000 miles from this third satellite. Okay, there's our third satellite, there's our 16,000 mile radius, here's the outline of our third sphere, so it must be somewhere on the surface of this sphere, but of course it must be somewhere also on the surface of the second sphere because it hasn't moved yet, and it also must be somewhere on the surface of the first sphere. So there are only two possible points that the GPS receiver could now be, and those 2 points are where the three gold circles intersect, up here and down here. So how does the GPS receiver tell which of those 2 points it's on? Of course, what it does is look for a fourth satellite in the sky, a signal from a fourth satellite, and only one of those points will be on the sphere around the fourth satellite. Okay? So you'll note, and it's shown here in this final figure, we've got four. This point is determined by the distance to a fourth satellite, and we've rejected this intersection of the gold circles out here. So now it knows where it's at this point here. Yeah, so only one of the points on the sphere will be around the fourth satellite. The important point to note is that at no time here did the GPS receiver know the direction to any of the satellites, only the distance. So it didn't calculate any angles, and that's why this process is called trilateration and not triangulation. Okay. That's all I have to say about an introduction to the basic concepts of GIS and one of the important tools that we have for determining our location, which is GPS. So if you have any questions or comments about the process of finding your location or about what a GIS is, then please put them in the question and answer window, and I'll be happy to answer them as soon as we go. Right now I'm going to turn the presentation back to Jenny, and she, I think, is going to talk about geographic thinking and how we'll use GIS to help us think geographically, and then we'll go on and have a look at an online GIS with Nat. Thanks, Jenny. Shall I turn the presentation over to you?
Yes, thanks. That would be great. Sam, there was just a question about the satellites if they were stationary, and so I think it's good to point out that the satellites that he's talking about are not stationary. They're moving along. They each have a fixed orbit that they follow, and they move along those orbits. If you have a handheld GPS receiver, a lot of times you can actually see which satellites your receiver is connecting to. It's pretty neat, because some of them show up with little circles and numbers, and that's satellite number 24 or satellite number 3 or 15.
Absolutely true. So the important thing there, Jenny, the satellites don't have a geostationary orbit. They do have an orbit that moves around the Earth. But the important thing is that we know accurately where they are in relation to fixed points on the Earth at any one time. So now if we know where the satellite is, we can then calculate the distance to that satellite and then place it on a point on the Earth. Does that make sense?
It does to me. If
it doesn't make sense, put us a question in the question and answer box, and we'll see if we can answer it.
Okay, somebody else asked a question about GIS versus GPS, the relationship. Basically, a GIS, you can't put information into a GIS unless you know where it occurs on Earth. And so the GPS is the tool that we use to determine location. And
Absolutely.
What's kind of cool about it is you can buy a GPS unit for less than $100, and your kids can get accurate coordinates for any place on Earth and put them into a GIS. And you'll be doing that this summer during the workshop. And you'll see, we're going to show you I'll show you some examples of things that people have studied using GIS in a few minutes. And some of them have data that kids collected, and some of them have data that were collected by professionals. But it's interesting that the data from either of them can be used in a GIS.
That's right. So as I mentioned, there's two components, Jenny, of a GIS. The first one is location, and as I mentioned, we can use GPS as one of the really important tools that we can use to determine where things are. The other important tool is the other important component of a GIS is what it's like there. And scientists and science teachers and kids have had a lot of experience, especially in recent years, of using scientific instruments to determine what it's like at any particular location. A pH meter, a thermometer, just using your eyes and describing something. All of those ways of measuring what it's like at a particular location, we all have a lot of experience in using. The power of using a GIS is when you combine those two components, where it is and what it's like there, and then comparing that over a geographic area.
Okay, I think that's good. There's a couple other questions. I think we'll get back to you soon, folks, if you've typed them in the question and answer window, but we are going to continue. Somebody asked what is
Thanks, Jenny.
Yeah. Am I muted? Can you hear me?
Yeah, we can hear you.
We can hear
Okay,
you.
good. Well, I'm going to continue then. Okay, geographic thinking. This is a quote that I found that I really like. It says, the location of everything is becoming, the location of anything is becoming everything. So what geographic thinking about and what a GIS does, let's see, is it all of a sudden we start thinking about where things are on Earth in relationship to maybe why they're there and where they are in relationship to other things. And so what the GIS does is once you know where something is, you can start looking for, well, where am I compared to everybody else? Why do I see, why do certain features occur at this place? And what sort of relationships do you see? I have a short, I'm going to try doing this. I have a short video. It's 5 minutes that I'd like to show you. I downloaded it to my computer, so this should work. But if it doesn't work, there's a link. The link is on my presentation, but it's also on the CoastLines site under today's forum. And it's a project called the Geospatial Revolution, and it's a short 5-minute video. And what I like about it is it's very powerfully shows you why geography matters and what GIS is. So I'm going to show you that. Let me see. I'm going to switch over to that. And I'm going to show you this. This comes across really crappy. Let me know, and I'll stop it, and you guys can watch it later. But it's just a very powerful, I think it's very powerfully shows you what GIS is before I start my presentation.
Want to know how successful your house is. So you put sensors on satellite, collect information, and then computers create maps. Okay, now you have a map, so you want to analyze that map. So you take information about the slope. Are you on a dead-end street? You have a lot of fuel around. Put all that information into a computer, and it can tell you how at risk you are for losing your home to wildfire.
Ever since the Babylonians etched the lay of the land on clay tablets in 2300 BC, mankind has needed accurate representations of the earth.
Maps used to be made from horseback in the 1800s. They took a long time to make. So we evolved to aerial photography, and that's made a huge difference with how humans understand Europe.
I'm showing the terrain. I'll bring them in. In the 60s, people began to think about the notion of encapsulating or abstracting geography in a computer. And people could look at the evidence and visualizations or analytics. That was just a magical idea.
Okay, this is very soft, but what it's showing you, this is Barack Obama swearing in. It was live satellite images, and it's showing you. I think I'll stop it. Can you guys hear it?
No, Jenny, we can't hear it.
Okay, I'm going to stop it then. But what I'd like you to do, this is one of your homework assignments, then, is to go onto this website and watch it. It's very powerfully shows you how a GIS works and what GIS is. And I think you can see from the first example that they have is what they were interested in is somebody was looking at their house and trying to decide how at risk they were for wildfires. And what they would need to know is, if you were going to answer that question, you need to know where you live. What's your street light? Are you on a dead-end street? Are there multiple ways to get out of your neighborhood? What is the vegetation surrounding your home like? What's it, as well, not just your house, but the greater community. How much rainfall have you had? What's around you? So it's trying to show you that all these information can be put into a GIS, and then people can use it to analyze data. So I'm going to just stop this video. Please watch it, and I'm just going to continue. Okay. So geographic inquiry, and Steve talked about this last week, and Sam mentioned it earlier. It's very similar to the scientific method. We're going to be asking you to think geographically, and we're going to try to model this throughout the webinars that we do that use GIS, and we're going to also try to model it during the summer when you come to Santa Barbara for the CoastLines Summer Institute. But what you do, and the power of a GIS is that it allows you to think and to ask questions and to analyze data. And we're going to have you do that, but we're going to try to get you to start by thinking of small questions. People tend to come up with questions that are way too big, but you need to start with simple questions and ask them. And then as you ask questions, you start to acquire data that will answer those, and we'll be giving you data to help you doing that. You'll be exploring that data, looking at, well, what does it look like if I put it on a map? Are there any sort of patterns that I see? Does anything come out if I start looking at some of the attributes behind just where things are located? You're going to analyze that information and then act upon it. So this is very similar to the scientific method that you're familiar with, and you can use the computer and you can use GIS to do those same things. So it's a very powerful tool. Okay, so what I'd like to do is I'm going to give you four examples of how a GIS works and to kind of use it to teach geographic thinking. And I'm going to start with, this is probably the classic, if you study GIS, this is one of the classic things when it was first used. In 1854 in England, in London, there was a big cholera outbreak. And cholera, if you know anything about what England was like then and what London was like, is that generally there was a lack of sanitation there. So that a lot of the houses were built on, there was boards, and underneath the boards would run the sewage. They called it the night waste or something. There was some term. But basically, sanitation wasn't that great. It was before there were sewers and things. And there had been other outbreaks of cholera in London, but what happened was in one community, it was a community center around Broad Street, there was a really terrible outbreak, and within a few days, a couple of hundred people died. And this is a small neighborhood. And so this outbreak caused panic, huge panic in the city, because at the time, the belief was that disease was spread by bad air. So there had to be something wrong in the air, and people just wanted to get away. And they did. They fled the area. About 3/4 of the residents fled the area. At the same time, there was a doctor. His name was Dr. John Snow, and he was interested, and he was studying the cholera and trying to figure out what was causing it and where it came from. And so some of the questions that he was asking is, well, where do these people live who are dying from cholera? You know, a very basic question to start with. Well, where do they live? What's around them? Why are so many people in this neighborhood dying? Why is it Broad Street? Broad Street was part of the Soho district. Why not another street? What's special about the street that's causing these people to get sick and die? And what habits do they share? Okay, so this is all the asking geographic questions. And what he did that, and this is what was pretty powerful at the time, is he took a map of the city, and this is actually the map that he used. And if you look at it, it is blurry because I enlarged it and it's hard to see. But what I want you to pay attention to is there's these really thin black lines, and you'll notice them all over the center of the city. And what these were was Dr. Snow partnered with one of the ministers in the area, in the local community, and he went door to door and started talking to the families and the people that lived there. And each of these lines represent somebody that died. And so there was lots of people that died. So he had this map, and he started looking at the community. And what you'll see is I've highlighted some things that I could see on the original map that you can't see on this presentation. But this tan streak is Broad Street. So it's not very big. This community, people would walk all the time. It's not a very big neighborhood. And all the big red dots were water pumps. Okay? And so what he started seeing was that most of these people who were dying lived closest to a water pump on Broad Street. And he didn't know why that was true, but when he saw this, it was very compelling to him. He didn't know why they were dying, but what he did was he took some action. He went and he showed his map to the local officials, He says, look, I'm not sure what's going on, but these people, most of them are dying, are closest to this water pump that's located on Broad Street. So the city officials removed the pump handle so that people couldn't use it. Okay. He also, because he talked to these families, started discovering that even though some people were closer to these other water pumps, what he found out was that people in these families that died used this water pump on Broad Street. Whether it was their children went to a school near this water pump and the kids used this water pump during lunchtime, or whether for whatever reason some of the neighbors just preferred the pump on Broad Street versus the other water pumps. Okay, and they died. They got sick and died. Okay, so what happened then was they removed it. The number of deaths decreased, and later it was found out that what had happened was that this pump on Broad Street was dug 3 feet from a cesspit. So there was actually harmful bacteria from feces and waste, human waste, that were leaching into the water supply, and that was what was causing people to get sick. Now there is some. By the time he published all this, the epidemic had started to die out because a lot of people left the area, but this is probably the first incidence of epidemiology where we use location and where people are to trace diseases. And this is probably one of the first known examples of GIS being used like this with a map. And it was all done in paper and pencil. There weren't any computers, but it was pretty powerful. So this is one story. Using where people are, where they're getting sick, looking at what's near there, and starting to figure out what's done. This was done actually this past year when the swine flu was going around. You could have seen maps that were similar to it, and people were using it, counties were using it. Okay, here's my second example I want to show you. This is Isla Vista this is actually a project that was done by students. Chip Fananga, who you will meet, who's participating in CoastLines this year. This is actually a project that was done by his students at San Ynez Valley Union High School and his East students. If you've ever been to Santa Barbara, Isla Vista is located just adjacent. It's just north, just past the University of California at Santa Barbara campus. And it's a very, very densely populated area. Okay. And as you can see, it's located on a cliff, and there's significant issues there that deal with erosion. And in the past, there's been a lot of litigation and confusion between property owners and Santa Barbara County officials, because the county officials have the probably the joyful task of condemning houses when they get too close to the cliff line and it becomes unsafe. And every year, or it's not uncommon to hear about students that fall off the cliff and die because these houses are built very close to the cliff. And it's not that they built them so close to the cliff, but it's that erosion has occurred since they were built. So the questions that Chip's students had was they wanted to look at, well, where is the present cliff line? Okay. Nobody had ever mapped where the cliff line was, so there wasn't a baseline to establish to say, here's where the cliff line is. Okay, so their questions, and these are some of the geographic questions they had. Where is the cliff line now? Where did it used to be? And can we tell how fast these cliffs are eroding? So what his students did, oops, wrong way. This is a picture I wanted to show you before I go on. This is actually an aerial photo I got off Google Earth, and so it's in color. This is, if you can see on the right, this is the University of California at Santa Barbara campus, and just to the left, this is the Isla Vista community, and here's an area that I blew up, and you can see these houses are located very close to the cliff. You can see the waves crashing below them, and there's not a lot of space in the backyard if they have them. So just to kind of give you a sense of what the area looks like from a bird's eye perspective. Okay, so here's what his kids did. His kids actually used GPS units, and they were able to track the present-day cliff line. So they were able to mark it, and it's shown on this map. This is an aerial photograph. It's shown on the map in blue. Okay. They were also able to go back and figure out what the cliff line was in 1975. So they were able to trace it backwards using records from the community that shows what the parcel lots were, the parcels where people had their homes, and there was old aerial photographs. They could have also used that to digitize the coastlines. And then, so they're exploring data. But what the powerful thing that the kids did was then that they were able to measure the distance between these two and get an erosion rate. They could figure out how fast the cliff was eroding. They could predict a 10-year rate in the future. Where would the cliff line be in 10 years? Where would it be in 50 years? And so on their map, you can see the purple line represents the 2015 cliff line, and the red line represents the 2055 cliff line. And you can see by 2055, a lot of these houses are in danger if the erosion continues at the present day, if it continues at the present rate. And so the kids were then able to share this information with the county officials. The county officials now have a baseline. They know where the present-day cliffs are, and they can estimate erosion rates based upon recent history. They can go back and reassess the cliff line if there's major events that would erode it. And they were able to do something useful for their community that was important. And so this information can then be shared by county officials, and they could use it for maintaining public safety. They can kind of have an idea how fast it's eroding. And the kids did it. It was pretty cool. And the whole scientific process. Okay, I'm going to stop for just a second and see, Chip, do you have anything you would like to add?
Hang on, Jenny. I'll have to unmute him.
Okay. And I'm just going to go back to see the picture.
Okay, Chip. If there's anything you'd like to add, Chip, you can go ahead.
Okay, I guess we're okay then.
Okay.
Oh, we'll ask him again later if he does. Okay, here's another ask. Somebody had mentioned this in the question and example. My third example, this is data that deals with the 2004 Sumatra earthquake, which was a 9.0, 9.3, depending on who classified it. But it occurred in the middle of the Indian Ocean and, of course, resulted in the widespread tsunami. We had a teacher that was teaching earth science that was interested in studying this. And so some of her kids, some of the questions that she had them ask was she wanted to find out, well, where did this earthquake originate? Where is the tsunami early warning system? There's supposed to be a tsunami warning system. Where is it located? Why wasn't it effective? How fast did the tsunami travel? And why was this area so devastated? So these might be some of the questions that she could use the GIS to ask. And what she had her students do is, there are many earthquake recording centers around the world. She got data from 3 of them. Okay, they were stations. I don't remember what the names of them were, but they were ENH, PULC, and so there were 3 stations. And what her kids did was she taught them to read the seismographs that came from the earthquake centers, and the kids were able to figure out how far each of these centers were from the earthquakes. And they did that. They got some distances, and then they were able to take the location of the earthquake center and its distance and put it into a GIS. And then they started, after they had this data, they started analyzing it. And this is kind of like what Sam showed you earlier, was the kids basically were able to create buffers or create circles around each location. Okay, so they're exploring the data and analyzing now, and they were able to figure out where the center of the earthquake was, and they could see it was just off of Indonesia. Okay, they could then take that data and look at the population, look at where people lived, and so the black dots that you see, and some of them are gray, and they're all over the screen or all over the map, are all cities in the area. The kids selected all the cities that were within a 2,000-mile radius of the epicenter, and those are these the red dots, and you can see that there was, some in India, some in Sri Lanka, and these were the cities that were probably first hit by the tsunami and at the greatest risk, because it hit so fast. It did travel across the whole basin, but they looked at this, and the kids were then able to figure out when the tsunami hit and enter that in and measure distances and calculate speed and study more. The other thing the kids asked was, well, why didn't we know about this? Why didn't we know that there was going to be a tsunami? We know that when there was, just recently, when the big Chilean earthquake happened, what was that, like less than a month ago? When that happened, I was on Facebook and I saw tsunami warnings go out, and I have friends that live in Japan, I have friends that live in Hawaii, and all of them were concerned about tsunami warnings. They had all received notice that there could be a tsunami. They were put on alert. Nothing, it didn't happen there, but they were aware of it. Why weren't we aware of it? And what you can notice from this map is all these red dots are the earthquake centers. They're pretty well spread out, and all the green flags represent the tsunami warnings, the buoy centers for the tsunamis. And what you notice is that the tsunami meters were mostly around the U.S., well, because we were funding them, and we were concerned about our coastline, but we weren't necessarily concerned about other people's coastlines. So what the kids were able to do with the knowledge is they could figure out the major cities, they could calculate the speed, they could communicate this, they could also look at vulnerability based upon population. And what the world found out is, hey, we need to be more involved. We need more tsunami warning buoys. And then there was an international effort led by the U.S. and NOAA, the National Oceanographic and Atmospheric Administration. And now there's a network of approximately 48 buoys that go all around. They're better represented around the world. So this is the current system right now, and you can see the red little triangles are all buoys that are owned and operated by the U.S. There's some by Australia, which are the yellow ones. There's one by Chile, purple one, Indonesia, and Thailand. Okay. So we've learned, obviously that we need to be involved more. Okay. This is just an aside along with recent history. If you're interested in the quakes, the Caribbean quakes, and you think, well, why gosh, I didn't know Haiti had earthquakes, or maybe you did. This is all the earthquakes that occurred in Haiti from 2004 through 2007, and the larger circles represent bigger earthquakes. So the big circles that you've seen on the screen represent earthquakes with a magnitude of between 5 and 7. So it is a very geological active area, and you could have the kids, if they wanted to find out what's there, why it's so important, if they put it over the plate boundaries and see the relationship, you can see that the Caribbean plate is very, very active as it borders up against the Cocos plate and the North American plate. Okay. All right, the last example I would like to show you goes back to California. And this is actually some of the data that we'll be analyzing later this summer and during one of the webinars. Okay. So this is just looking at exploring the Santa Barbara Channel. Okay. The Santa Barbara, for those of you familiar with the area, it's a very biodiverse area. It's very, very species rich. And one of the reasons this is true is because it's a transition zone. It's an area where the warm currents flow up from the south and the cold currents come down from the north, and they meet in the channel. And it causes the channel to be a place where it's the northernmost limit for some species, the southernmost limit for others, and it's just a very species-rich place. It's the Santa Barbara area. It's an international biosphere reserve, and it's been, as well as a national marine sanctuary, and it's a long-term ecological reserve site, and there's national parks there. It's a very special site biologically and ecologically, and so it's a very neat area because of all this diversity. And it's actually been described as the Galapagos of the Americas, just because of the species richness that's found there. So if you were studying the Santa Barbara Channel with your students, you might start to see, well, if it is a transition zone, what does that mean? And so some questions you might ask would be, well, what are the sea surface temperatures like within the Santa Barbara Channel? How are they distributed? What's the range? What evidence is there that it is a transition zone biologically? Do I see some species with their northernmost? Can I find species that I can look at and find out that this is the northernmost place that they go, or that this is the southernmost place? And if all the species richness is determined by temperature, what impact does an El Nino event have? Because currently we're in an El Nino, and so what impact does that have? And there have been El Nino events in the past. So there's a lot of questions that people can begin to ask. Okay. This map shows you the average sea surface temperature in degrees Celsius for July of 2000. The yellow temperatures represent warmer waters. The blue temperatures represent cooler waters. And you can definitely see that the warmer waters are in the south, and the colder waters you can see the colder waters coming down from the north. Okay. We talked about a GIS being lots of different layers that you can put over it, and you can overlay together. So we've added some layers here. Besides just the sea surface temperature, there's some blue lines and red lines, which represent the major currents. The blue lines are the California current. The red lines are the Southern California countercurrent. They're bringing warm water and cold water into the region based upon their colors. And there's some of those cities, the major cities along the area are named. Okay. And the thin blue line you see around the islands is actually the boundary for the sanctuary, Channel Islands National Marine Sanctuary. And there's a really thin one for Channel Islands National Park. And then the LTR site covers it covers a lot of the watersheds surrounding the Santa Barbara Channel and that feed into the channel. Okay, so then as you start exploring data, which you would do with the GIS, you might say, well, I want to see what the sea surface temperature looks like over time. And you might have collected sea surface temperature. In this example, we've collected sea surface temperature from 1997 to 2004. And they're all individual layers on the map. You might say, well, what's the temperature like at a specific spot? And Sam mentioned that a GIS is tied to a data table. And you can see that here, that there's a table, and if you look at it, it gives you the year and it tells you what the temperature was. It's 15.9 degrees, it's 15 degrees, it's 16.65 degrees, it's 15 degrees, 17 degrees, it's gone up a lot. It's 16 degrees, it's 16 degrees. And so it tells you you can get the information from any specific point, and you can also, if you're interested in analyzing it, say, well, what's the average temperature like? If it changes every year, well, what's the average? And this layer has been, all those data layers have been averaged together, and the computer does it for you, and it kicks out an average, and it shows you what the average temperature is. Now, it's not as pretty as the other sea surface temperatures that you looked at because there's these gray areas, and that's because some years we don't get data for the whole map just because of cloud cover that interferes with the collection of the data. And so those are points where at one of those years there was clouds interfering. So then you know what the average temperature was. Well, 1998 was the last El Nino year before this one. So 2010 is an El Nino year, and 1998 was the last one. If you want to know, well, what does that mean for Santa Barbara? We know that there's warmer temperatures. You can actually compare the temperature in July of 1998 with the average temperature you've just done and subtract it. And the computer does all this. And if you change the legend, you can actually have it display the data so that red temperatures, darker reds, represent places that are warmer. And I think the dark reds are like 5 degrees warmer. White is same, and blues are colder. So you can see that the whole area was generally much warmer than it normally is, especially to the north. So the warm water masses were pushing upwards. And again, if you keep asking questions like we do in science, you do experiments and you ask more questions, you go, well, what does that mean for fish that live in the area? And you might that might be your question. And so now you see these little black dots added, and these were sampling sites that are monitored by that are monitored in the area by the Channel Islands National Marine Sanctuary and the National Park and other interested partners. And they look, there's actually sites throughout the islands, but they were looking at the distribution of Garibaldi, which is this bright orange fish. It's a California state fish. And what you see is the fish is only found in the warmer waters. It's not found on the north end of San Miguel Island. It's not found on the north side of Santa Rosa Island. You see it all the places where the waters are yellow or blue, or that they're warmer. And you start to say, I wonder if temperature is affecting the distribution of this fish. And you can start to see that, yes, it is, and the kids can do that. And so what the kids can do then is they've investigated the impact. They've done several things, and you could pick any one of these for a project. They've investigated the impact of an El Nino on the channel. They know what a transition zone means. They understand more about the ecology. They can understand how sea surface temperature affects the distribution of a fish. They can do a lot, and then they can communicate the results. And something like this, maybe instead of telling the community, they might make a lab report or a community presentation, or share the information with their classmates. But again, they've gone through the scientific method. They've collected, they've asked questions. They've collected data. They analyzed data. They've gotten results, and they've done something with it. So just to recap what my big message was, is geographic thinking is, when you teach about it, you're really teaching about geographical importance, why things are where they are. What sort of evidence interpretation do you see when you look across things? Are there patterns where things are found, patterns and trends? You're looking at interactions between things. It might be temperature dependent. It might be depth whatever it's dependent on. You're looking at using GIS to find a sense of place. And sometimes there's even value judgments that can come out. And so keep those things in mind. Keep in mind that really it is the scientific method. What do you want the kids to explore? What do you want them to do? And keep in mind, like the scientific method, when you do sciences, sometimes it's messy. It's not always easy to get your experiment to work right. It's not always easy to get the data to work, and sometimes our results aren't clear. But that's part of the learning and the thinking and the process. Okay. So that's the end of what I wanted to say. Are there, maybe should I see if there's any questions real quick before are there any major questions?
I have a question, Jenny. Somebody wrote in and asked if they could collaborate with a colleague at the same school on the same curriculum to investigate the same question. Yes. We highly encourage people to work together in teams, because we find that people are most successful because this is messy. Sometimes there are challenges, and it helps you to be successful, and it helps your kids to be successful if you work with somebody else. So yes, we highly encourage you to work together, and we'll be giving you a lot of examples throughout the webinars. We'll be giving you examples this summer, and eventually we're going to ask you to take something that we've given you and modify it and make something that's usable in your class. And we'll also give you additional data sets that you can explore around the Santa Barbara Channel. So be thinking about what sort of things you might be interested in exploring there. We're going to focus on kelp forest and watersheds and sandy beaches is what we're going to be looking at. But just put that in the back of your mind. You don't need to worry about it right now, but just think about it. And as we work through different activities with you, and as you hear different things in the webinars, there might be something that piques your interest, and you think, hey, that's really cool. My kids would like it if I could do this with it. And that's what the powerful is. We give you data, and we might give you an example of one way to interpret it, but there's other things that other questions you can ask using the same data set. And keep that in mind. Okay. What I would like to do is are there any other questions? If not, I'm going to turn you over to Nat.
Okay, am I unmuted?
You're unmuted. Let me give you my screen.
I pressed the button to show my screen.
That's because I have to give it to you. Oh,
Okay.
Maybe you changed it. Okay. Unless you change presenter. Nat. Okay.
Nat, it's coming over to you.
Tell me when you can see me. Okay, in this session,
Okay, we can't see you yet. Give us just a second. Nat, I think you have to click the button that says show my screen. Did you do that?
okay, you've been made. Show my screen. Got it.
Here.
Now, I have two monitors. Are you looking at the screen with the map?
I can't see anything yet. It says waiting. Yep, we're looking at the screen with the map.
Okay, because the other one has got, the question screen on it. Okay, I get to show you about this neat program that was new to me this last couple of weeks, and I got to spend a lot of time exploring it. That is, in the next half an hour, I'm going to get everyone building a map that shows what GIS is all about. And a lot of what Jenny's examples were shown on is the program that we're going to be using a lot called My World GIS. But this one is online. The learning curve is very small, and in 15 minutes you'll be starting to build your own maps, and your students can have accounts and they can be building their own maps. In fact, you can teach an entire lesson with GIS inside of one regular class period. They can sign up for it just like you can. They can continue working on their projects at home, and then they can post them where you can see them or where other people can see them. Scribble Maps is actually not part of Google Maps, but it uses Google Maps as the background map, and they kind of work hand in glove with each other. And what I'm going to do is walk you through several steps of getting involved, and then I'm going to let you catch up with me, and then I'll get you back and then take you through a couple more steps, and then I'll call you back, and then I'll keep doing another couple of steps. I call this the Pete Seeger approach. Okay, so if you can have both the webinar in one location and also get your browser going, what I'm going to do is get you to type into your browser right here where it says scribblemaps.com. There's also a link on your assignment page, but you can just type in scribblemaps.com, and when you do that, I'm going to actually keep showing you, so just hold off doing it until I get a few steps ahead of you. You'll come up to the screen that looks like the one I'm showing. It says Welcome to Scribble Maps, but down below is this giant freebie. It says Try Scribble Maps Pro for free. And so I'm going to get everybody to, in a minute, to click on the link to try Scribble Maps Pro for free. And in theory, if I'm still connected, will load me into it. It says connecting, waiting. And you'll notice that the address above changes to puts the word pro dot in front of Scribble Maps. And if this would be a good place for you to bookmark this site if you're on your own computer or want to get back to it on the same computer, because this is where you will be coming in time and time again to log in and get started on maps in the future.
Okay, I'm going to interrupt you just for a second. You may have to register for Scribble Maps Pro, in which case it will send you an email.
Yes.
The difference between Scribble Maps Pro and Scribble Maps is that Scribble Maps Pro does more stuff. It's got more tools.
And in fact, you can register tonight. It takes seconds to register when I get that screen up. I don't know why it's coming so slow.
I think because you registered. You're on it.
Well, it says I'm still loading here. But when you register, you basically choose a username and a password, but it also wants an email address from you. And to register, basically, once they get the email address, then they'll send you a confirming email. And the confirming email simply means that you have a real email account, and you have to click on that email to indicate that you received it, and then you'll have all the features of Scribble Maps Pro. Now, it's coming real slow. I don't know why. Let me eliminate some things on the side. since I seem to be being slow at this, wait a minute, now it says it's reading maps. Now, do you see, does everybody see that username, password, login screen and register for free? And what you would do, because it's your first time, is click on the register for free. You have your username, a password, you confirm your password, the all-important email, because that's where they're going to send you the confirming. And 2 people that I have helped do this on Macs had trouble getting that email. And because they had trouble getting that email, what they had to do was email the support location and tell them they didn't get the email and please send it again. And they said, oh no, we'll just confirm you and you now have all the features of Scribble Map Pro. PC people don't seem to have that problem, so they're ready to go. Now, somehow I went backwards.
That's okay, 'cause people are probably logging on right now.
Okay, good for
So
them.
we're fine.
Okay, so I'm going to log in at the same time while you're logging in. Okay, I'm logged in. And Jenny, should I go on or should I let people log in and maybe a couple of them could say that they're logged in? Or
I think what we want to do is let them, okay folks, if you would turn over, flip back to the GoToWebinar presentation. And I think what we want to do first is Nat's going to just kind of show you a little bit about the site.
That's right.
And so just pay attention to showing him. Then we're going to stop and give you some minutes to explore the site. And when we do that, that would be good that you'll be able to go back and log on and let us know. If you can't log on to the site, just get onto the regular site because you'll be able to do some of the stuff, and that's fine, just to explore it. And that's really what we want you to do.
And if you follow along with what I'm doing, and then you follow along the handout that I gave, if you get lost because of technical difficulties, you'll just be able to follow the handout I gave you and do the same activity on your own. But the first thing I wanted you guys to do is to type in the address for your school, or you can choose the address for your home. And so if I'm fully up and running, I can type in the address for my school, and that's in West Hampton, Massachusetts, and then hit the little find button, which is an hourglass, and it should try to find the location. It first brings it up in what they call map. You see at the bottom of the screen there's about 4 different choices of the kinds of map, and it brings it up in map and with a little label. You click on the arrow button, and then you can click off the label by clicking that little hidden X. Then if you want to zoom in, they have a zoom in button right over here, and it lets you zoom in at your home or your school site, which I'm doing here, and I'm hopefully going to switch it over to satellite view so we can see what it looked like a couple years ago. And here's a satellite view of our school. Here's the school building. I'm going to zoom in a little bit closer. And so I want people to be able to build a layer. One of the things you're going to need to learn how to do in my world and all GIS is to work with layers. And what I'm going to have you do is sort of highlight around the property of yours approximately, or if you know the boundaries of your school, I'm going to use this connected line tool here and start it here. And I see how quickly I can build a line around my school.
Okay, the line's not showing up yet.
Okay, because there's a little bit of a delay between my screen.
Now we're starting to see it.
Okay.
Yeah, it's slowed down here too now. It was probably about a 10 or 15 second temporary stop between when you saw the satellite image and when I could actually see it on the
Okay. Now, to finish a line, it gives you a little notice that says you double-click when you want to finish the line. And now I have for me, it's a red line around my school. But important is over here on the side indicates that we now have a layer sitting on top of this satellite map. And we can click the map button and switch the layer underneath it and switch it back to satellite. The layers can be switched without changing your lines on top of it. Okay. Now, once you've got an outline and a layer for your home or your school, you can type in UCSB, and somehow they know that that stands for University of California, Santa Barbara, and you can hit the Find button, and this is how long it takes for it to find where we're going to be this summer. Again, you take the arrow tool, you click the X to get rid of the label, you use the zoom in tool, which looks like that little dotted line around a rectangle, and you can zoom in at where the, as soon as I click it, you zoom in around the University of California, Santa Barbara campus, and it zooms right in. Then, what I'm going to have you do is again use that connected line tool and do a rough approximation of the Santa Barbara campus. And so you've created a layer for that structure as well. And once you have layers, then you can switch back and forth between campuses. Okay, so can you now see the red line around the University of California, Santa Barbara campus, Jenny?
Now we can, yes.
Okay, now you don't need to do this, but look how quickly I can switch back and forth between the two layers. And so you can switch that way. Now, one thing I wanted to do was let you use a measuring. Hello?
So measuring? Okay.
Want to do measuring now, or should I give people a break?
I think we should let them find their school,
Okay.
their home, and maybe draw a line around it.
Yeah, because if you draw a line around it, the important thing is that you create a layer off to the side, which is what we're trying to do, is make these layers on the side. The two that I made are line layers of property lines. So we'll let people go ahead and complete those two assignments, and then I'm going to show you how to use the measuring tool. Now,
if you have questions or you're stuck, you can type a question in the question window, or you can, is it *5 on their phone, Sandy?
5-star. Yeah.
5-star on their phone, and it will raise your hand, and we can ask your question. But use the question window first, okay? And take a minute and play with it, and see if you can find your community. If you get it, let us know. Just send us a positive, instead of sending us a question, say, hey, I found it, and send us a positive message using the question and answer window. If you want to switch views on the map, at the bottom of the map window, there's 4 buttons.
Here's the map button right here, and that's sort of a street map.
Why don't you
Terrain is
them and let them and show them, but you need to wait about 20 seconds or a minute between it so they can see.
okay. And the terrain choice is kind of like a topo map. A hybrid is to put street map type data onto a satellite map. That's what Jenny showed us when she showed us this campus before, where she had the satellite view with all the streets labeled. It's called a hybrid view. And this is the satellite view that Google Earth or Google Maps puts out for free. Now, in case there's a few people that are just following along and are not working on it, I'll do a little activity just for those people. I'm zooming in on an area that to me looked kind of like a soccer field. And
Matt?
Yep.
Before you do that, somebody has a question about how you get the, when you switch between the two areas. They want to know how you know that there's like how it makes it a layer. So how do you get the line to save on the right-hand side?
Okay, as soon as you complete your line map, and you complete your line by double-clicking the line, it should show up on the side. Now, this button here would go to full screen, and this button here that looks like two little arrows pointing towards the right will hide that layer. As if I click that, I hide the layer, and I'm going to click it again, and it's going to show up. So if for some reason that's been clicked in that panel on the right-hand side where all the layers show up, this will hide it. You can always show it by clicking on that little button with the two arrows. And what switches back and forth is this blue tool here. It's called the centering tool, and it will center it in that layer so that one layer is the property of Santa Barbara, the campus. That for me, it's the top one. And the second centering tool is the property line of my school, and it will center it at the enlargement that you currently are in. So you can just jump between your layers very quickly. I'll do this quick little measurement. It's kind of fun for people that are just watching and they're not following along. Here's a line measuring tool, and I found a soccer field. And I know that soccer fields are about 100 meters long. And I'm going to see with the measuring tool how close it is. And you click it once, and it stops the line, and you click it again, and it places where you want to put the actual number of the measurement. So I've clicked it twice, and my quick measurement of that soccer field says 96 meters and 57 centimeters. And so even at that enlargement, it's fairly close. I could zoom in a lot closer and make it more accurate. The editing tool is the arrow tool, and you hover over a line and you can move it. And it made it even a little bit more accurate. Okay, it's hard to not to know where people are.
On their comments, a lot of people are doing it. A couple people have a question over which tool they're using to draw the line around their campus. So
Okay.
I think they're still finding their
I'm
campus.
going to hover the connected line tool, which looks like a letter Z, and it's way over on the left-hand side. And you use that tool to draw the campus. And you can do it quickly. You can just, like, I'll go right around the airport here. And that could take 15 seconds. Remember, it says to double-click to end the line so you don't keep on drawing as you're on to something else. So again, it's the connected line tool for doing the lines. The squiggly S tool is good for just scribbles that you just keep drawing until you double-click, and then it will stop doing the line. So if I use the scribble tool, I could draw a circle around the campus like that. Double-click.
That's more like
the
a
line.
free-form line type thing that they may be used to.
teachers could use that to simply put a circle around something they wanted students to see as they were projecting this. Okay.
Okay, there's a couple questions, Nat. One question is, when you make a measurement, where do the measurements show up?
Okay. I'm going to make a measurement and show you that. And what I've done is I've backed out my screen so I can see the California coast and also the Channel Islands. And I wanted to find out how far Santa Barbara is away from the nearest Channel Island. And so I'm going to use the line measuring tool, and I'll hover over that tool for 15 seconds, and then click on it. And now I'm going to click from my red marks over here indicating Santa Barbara and draw the line down to the island. Now, the first time you click sets the line, and the second time you click sets where the measuring line is. And here's where the measuring numbers is. So let me just do it from another one. Wait a minute, I'm going to have to get back on the measuring tool. And I'm going to go from here down to here. It sets the line on the first click. And then notice I can move where the numbers show up.
The numbers show up on the line.
Well, they show up next to the line, and you could move them as far away from the line as you wish. It sets up a parallel line that has the numbers. So I set it a second time, and now I have the measuring line, which is straight, the numbers line, which is in kilometers, indicating that it's about 39 kilometers from the shore to the Channel Islands.
Okay, there's one other question that I don't know if other people are having the same problem, is that they drew the shape, but it didn't create a layer file for them. So I'm understanding.
For most people, that occurs if you didn't do the final double click.
Okay.
And as you can see on my screen, I have layer files for all my scribbles, all my lines, all my measurements. And
so they should try selecting the line again and just outlining it again and just making sure they double.
If you have a line that you want to erase, you go over to your layers area. You just click the trash can, and it will remove the layer that you don't want.
Oh, that's nice. It highlights it first before it deletes it. Oh, maybe it highlights it as you delete it.
It will also highlight it if you wanted to edit the line using the arrow key, that you click on the arrow key, and when you hover over the line, it will highlight what you're going to be editing. Okay, let me see if I can get some of these questions that are coming up.
They seem to be doing okay. I don't see anybody that's completely lost unless you haven't sent us an email and said, help, I'm stuck.
Okay, so what I want to do now is zoom out using the zoom tool, which is very similar to, it's the exact same one that's Google Maps uses and Google Earth uses, and you just keep clicking down until you zoom out. You can try using the slider till you zoom out till you can see the entire United States. If it comes up like mine does and it's centered on Santa Barbara, you can click on the hand tool, which is a position tool, and you can use it to position your map so you can see the entire United States. Because what I want to do is measure the distance from Santa Barbara back to your school. And to do so, you use that line dimension tool. It's at the second row of your main toolbar over on the right-hand side. And you click that tool, and you make a click where Santa Barbara is. You can still see some of your red marks. And you click and hold and drag it over to where you happen to live, which for me would be over about here. And then you make the second click where you want the dimensions to show up, above or below the line. You can move it back and forth. You can put it close to one side. I like to put it on some part of the map where it's fairly easy to read it, with the background image not making it difficult to read. Once I've done that, I'm going to zoom back in on Santa Barbara. And I can see the end of my measuring line isn't actually touching the campus. And so I'm going to move it by using the editing tool, which looks like an arrow pointed upwards. You click that once, and if you hover over your measuring line, you can see a white box at the end. You click and hold the box, and you can move that measuring tool exactly to where you want the end to measure. Once you've set the end at Santa Barbara, you can hit the centering tool. That's your property lines for your school or your home, whatever you chose. And it will zoom you to that part. You can see your property line. You're still using the arrow tool. You click the end of the measuring line and click and hold, and you can bring that back and bring it right in on your property. Then you can click the zoom tool to negative so you can see the whole country. Of course, if you're a Californian, you don't have far to zoom. If you're from East Coast or Louisiana or Michigan, you can move to the whole country, and you can see how far away you'll have to be from your home or your school when you're taking the summer course this summer. For me, it's 4,142 kilometers. There's a little X always in the center of your screen that shows where you will go if you zoom in, so you can use the hand tool and bring the X right to where you want to go, and simply zoom in at that spot, and it will stay centered right where you. I'm going to move my line here over to the campus. I'm going to move Santa Barbara into the center. I'm going to zoom in till I can clearly see the campus. And I'm going to use that connected line tool to redraw my campus, because I had erased it earlier by accident. Double-click when you're done. The editing tools for these lines are absolutely extraordinary. You can get in and edit very fine points of editing. You may not want to do that tonight, but I can do you a quick show of that by showing you just one tiny little area of the map. I'll put the top of the campus in on the X, and I will zoom into it so you can see where my mistake is that I can re-edit. And then you switch on the editing tool, which again is that arrow, and you hover it over the line, and it shows you squares, which are points that you have placed, and circles, which are halfway in between the points that you've placed. But if you grab a circle, it turns into a square, and you can move it. So you can move both the squares and the circles, and you can edit down to the inch on the ground if you spend the time and want to get things done very accurately. Then you can zoom out and check your handiwork. If you've caught up with me and you're waiting for me to go on, I can just have you have the fun of grabbing that measuring tool again, the line dimension tool, and you can see the airport over Santa Barbara, and you can check the length of the runway. The east-west runway seems to be 1.88 kilometers. I think you can have a nice safe landing there, and you can use the same tool to measure the north-south runway. However, that one's only 1.2 kilometers. I hope the wind is blowing east and west if we land there.
Hey, Nat, we've got a question from a couple of folks.
Okay.
Is there an easy way to change from kilometers to miles?
I've seen it done in both, for example, square kilometers and acres, but I actually haven't explored that, but my guess is it would be done in the preference panel. And so I'll have to answer that question if you post it in the forum, because right now I've just kept it in scientific in kilometers.
Okay, thanks.
But I've noticed if you measure the area of a small area, it will give it in both acres and in square meters. So we can try doing that. To measure the area of something, we have this tool over here that says measured polygon, and you can pick like these soccer fields right here. I got the wrong tool. Measured polygon, and you can draw a polygon by clicking on corners of the polygon, and you will grow the shape of it. And when you complete it, it will tell you how many square meters and how many acres your polygon is.
Okay, what we want is, we have about 15 minutes left, Nat. So what we want to do is, folks, what we wanted to do with this was to give you a chance to just start playing with some online mapping. And we picked Scribble Maps as opposed to Google Earth, which some of you may be familiar with, because there's a couple of reasons. One, you didn't have to install Google Earth on your computer, which sometimes installing software is a problem for people. But we also like the fact that it was in some ways like a beginning GIS unit, that there was different layers that you could switch from. You could switch between different map views and see whether it's an aerial photograph or a topographical map. You could interact with it and create these little layers, and it saved them as layers because you're going to actually be hearing about layers a lot over the next year. You could do some measuring and get some areas, and you could start to get the sense of how a GIS works. Okay, so don't worry if you didn't get everything done that Nat showed you.
And you can follow
He has a great handout for you that if you want to go back to it right now.
And the one thing we should leave them with before they're on their own is how to go in. You hit the menu button, and you come up with a menu that has some 21 choices, but in it is the Save Map button.
Okay.
If you don't save the map, then you can't get to it later.
Okay, so folks, if everybody would switch back to the webinar presentation real quick and just watch Nat. He's going to take about 5 minutes and show you a few things. Don't worry about doing this right now. Just pay attention to Nat. He's going to show you how to save a map, and he's also going to show you that the cool thing about this is you can add your own data in or add a shapefile, and if you have a shapefile, and and it will display it. So we're going to take just a few minutes and just watch now. And this is kind of a, wow, that's cool. I wonder how I do this. You can get to that later, but just be aware that you can do it. So right now, just watch Nat and be awed. Okay, Nat, it's your turn.
Okay, so you can be anywhere on your map. I'm in the Santa Barbara end, and you hit the menu button. And it gives you a lot of choices, and some of them will be more important to you later on. But the first one you need to learn how to do is to save your map. And when you click on it, it gives you a place for title and a place for description. And you actually have to fill in something in both areas. It doesn't care what you fill in. You could put in anything you want, or you can take time and put in a real description. I just put in SB for Santa Barbara, and I hit save. And it's now transferring it to what's going to be your space on their server. They may give you a secondary question. Are you sure you want to save the map? You hit yes. It dims the screen while it's saving. Now your other choices is you can save just a picture of where you are now. If you've made a map and you don't want them to move all around the country, and you've just like the one that it's Santa Barbara, you can save just the picture now by hitting the Save the JPEG. It will tell you its address, and you can access this. You can send those addresses to people by email. You can put them in on websites. They can access it. But more importantly, you can access it yourself. You go to File Manager, and you have a choice between Files and Maps. And over here, you can see my SB map, which I just saved from tonight's webinar, and you can see these various choices that I have already previously saved, and you can load any of those at any time. You click the X to get out of that. And what we want to show you now that makes this a more of a full-functioning GIS program is that you can actually import data and import shape files that you'll learn how to make this summer. But you can import data in the form of Excel, and what you first need to do is to import it to your file manager. And so if I click my file manager, I have data which is in the form of Excel spreadsheets here, and I seem to have 5 of them. I've got shape files here. And so I'm going to bring in a shape file that I call Spring, and I'm going to import it to the map. And this is data that Jenny sent me that she collected about the latitude and longitude of migrating gray whales in the springtime. And she's got 2 files she sent me, is where they were in the springtime and where they were in the winter time. And you can see in the map behind me, we've got circles with little X's in it as to the latitude and longitude done by crew members of a certain boat. And if you zoom out so you can see the whole channel, and wait for the map to catch up with you, you can see where those, as soon as it catches up, it's in the process of catching up, it will start displaying those red dots. And so what I've done is brought over a shape file that was made by My World, the program you're going to be using a lot this summer.
Okay, our map hasn't caught up yet. I see it, but I don't see the layers. I don't see the shape. Oh, you haven't. Never mind. I'll shut up. Okay, what a shape file is just a layer for a GIS unit, and it's a format that's just like a document deals with Word files. This is a shape file is it's a type of a file. It's actually a collection of files that it's used to display anything that's represented as a point, line, or polygon on a map. Okay.
Okay. Can you see the round dots now? I mean, the round circles now?
I don't see them.
They're visible on mine.
Now I see them.
Okay. There's about a 15-second lag I got to get used to. So what I did there is brought over the data of the location of gray whales that happens during the spring, And as Jenny points out, they seem to hug near the coast. And one of the theories they hug near the coast is it's more protected there. There's a major shipping channel that brings big ships through here, and maybe there's predators that they have to worry about, and so they tend to hug the coast. And
Yes,
another,
that's particularly true. The gray whales migrate from the Arctic all the way down to Mexico where they have their calves. And on the way back, they bring their young are traveling with them. So the young whales are preyed upon by killer whales or probably killer whales. And so if they're close to shore, the blue whales are close to shore with their babies. The babies are protected because the water is shallower and it's a little bit safer for them.
and then, so that's showing you how you can insert a shapefile. And the next thing I'm going to show you how to do is to go back to the menu, back to my file manager, and I want to try bringing in a spreadsheet file. And I did spring, so I should try bringing in a winter file. And you can either bring in a regular Excel spreadsheet, and the suffix for that is the XLS, or you can bring in what's called a comma-separated value file, and you'll learn how to make that. So I'm going to try importing that one. Now, when you load a spreadsheet file, it wants you to tell them which columns certain kinds of data is stored in. And looking at this file, mine is loaded, but I'm looking at the F7 column seems to be the latitude, and the F8 column seems to be the longitude, and our area longitude, of course, is negative. And so down here, you simply tell this program that as you import all this data, these are the attributes that we heard about earlier, be sure to indicate that the latitude is the F7, double check that, the 33s and the 34s, and the longitude is the F8, that number, and all this other information won't be displayed. You can play with the different markers. It says you can change the marker. What I do is make the marker really small because we have a whole lot of data here, and hit Add to Map, and you can put it away. And it should be transferring that data through the Internet because I had stored it on their server, and my computer says at the bottom that it's transferring the data. But you'll see that it will display it differently, so you can see the differences between the migration patterns in the in the spring and in the winter. And it's still taking a few seconds to load. But what you'll see is that the migration is mixed, but a lot of it will be closer to the Channel Islands.
And we're still waiting for the map to refresh. So folks, I think part of the reason why it's slow is because we're running a program over the Internet on top of the GoToWebinar software. So we've got double delays.
When you do this by yourself and not using the GoTo program, you should have much higher speeds for this. So it's kind of like going to the Internet twice. Now, just while we're waiting for it to load, if you look at the red square on the top where it's next to 80, all the things that we've loaded have been red, all the lines have been red, but you can change the color of anything you want, and if you've already made it and it's red and you want to change it from red, the editing tool for color and names are that little pencil. And we're going to use that same pencil in my world to indicate that you want to edit things as well, so that must be a universal symbol. And if you click on that, you can name the layers instead of measured polygon. You can call it the soccer fields, and the measured line could be distance to the Channel Islands or distance back home. You can change that title, and you can change the color at that time.
Well, we're still waiting for it to refresh, but I just want to thank you, Nat. Okay, folks, let me just give you an overall picture of what we've done tonight. Okay, don't panic if you haven't kept up with everything. Here's the take-home message. GIS is a smart map. It's smart because you can interact with it, and you can get to the data behind it, and you can do different analysis with those data. tonight what we've tried to do is just to show you a little bit about what it is, kind of give you some examples of how it's used, and to let you kind of just start playing with it. One of the first things people have to do when they work with any sort of GIS is just get used to moving a map around and getting used to switching between what you can see on the map, the fact that it's dynamic. And so that's what you've done tonight. You've done some zooming in, you've done some zooming out, you've typed in addresses to have it go find things, you were able to draw lines, you were able to measure things, you were able to switch between what your map looked like, whether it was a map or terrain or a satellite view. Okay, so those are a lot of basic skills that you use in a GIS that, if you haven't used a GIS before, are overwhelming. And if you have, they become second nature. You start to know how to do that. Okay, and it doesn't matter what sort of system it is, whether it's Scribble Maps, whether it's Google Earth, whether it's My World or ArcView or ArcGIS or whatever it is, you start to learn how to do that. Okay,
You'll
so our goal
also
is just to introduce it to you.
And you'll also be making these shape files, like the first one I loaded, the one you see that's in red. You'll be making that this spring and in this summer, and those same shape files you can use in lessons where you just want the kids to use Scribble Maps, because they can be downloaded from the internet directly into their maps. So these two programs will work together very well.
Okay, great. What we need to do is it's 6 o'clock in California, 9 o'clock here. So what I'd like to do is to take a few minutes and give you some announcements, things that you need to be aware of that are coming up.